Thank you for coming today. We're having a little technical difficulty, but we're very pleased to have Anthea who's going to talk about tropical geometry of phylogenetic tree space. Take it away, Anthea.
Thank you very much for this invitation to speak, and thank you again for your patience for these technical difficulties. It's extremely frustrating, but I'm glad we finally made it, and hopefully this will keep up for the talk. So today I'd like to talk to you about one area of my work, which involves exactly phylogenetic trees from the perspective of a variant of algebraic geometry known as tropical geometry, which I've done quite a bit of work on. So most of this talk is going to be trying to sort of explain the motivation in the situation rather than sort of focusing on any particular result that is mine, even though I will sort of overview what I've done in the area as well. But I'd more just sort of like to, kind of explain the general setting and kind of give you a flavor of why I think that this is an interesting area to work in. So the background here. So I'm been working with biologists for a while, and where I'm interested in phylogenetic trees. So they work with a lot of evolutionary data, and this is captured in the fundamental model, which is a phylogenetic tree. And the idea here is that it's a graph that basically captures evolutionary behavior. So this can be sort of like speciation, as in like the Darwin's birds, or it's also used to measure the spread of pathogens, viral evolution, cancer evolution. Pretty much every single evolutionary behavior in biology is captured by a phylogenetic tree. And so these are very important data structures. I mean, they capture all kinds of different relationships in biology, and it's really important to understand how to work with them. But they are difficult to work with because they are discrete geometric structures, and moreover, the collection of all these trees is a non-Euclidean tree space. And in particularly in biology, these trees, they can also become very, very big, right? So, we would definitely be working with a sort of big data context here. So, right. So essentially it's an evolutionary tree where the relationships between taxa are related by a common ancestor. So there's a common ancestor from which basically we have a divergent evolution, and all this relationship is basically documented in this tree. So a bit more mathematically, a bit of notation and terminology that I'm going to use throughout this talk. So big N is going to be the number of leaves of our tree. And I'm going to denote by the brackets of big N, just sort of the collection from 1 to N of their leaves, little n to be big N choose 2. So an N tree is just a tree with N leaves. And we have a binary tree where you have a single root. So a root is unique, and it has a degree 2. And if it has degree 1, then it's a leaf, and if it has degree greater than 2, then it's internal vertex. So the number of binary N trees, there's known to be 2n minus 3 double factorial, many of these. And a metric entry is one where there's a non-negative weight on all of the edge lengths here. So a metric entry is exactly what a phylogenetic tree is, and it's exactly the object of interest in this talk. So edges connecting to leaves are called external edges, and everything else is called an internal edge. Right? So a little bit of motivation. So where do these phylogenetic trees come from? So the idea is that you have some kind of input. So you have an alignment of sequences for N species, right? This can be DNA, RNA, for example. And then essentially there's like this construction process, and then you would like to output a phylogenetic tree, which basically gives you sort of the relationship between all of these species, the inputs here. So this is not the focus of the talk today, right? How to build these trees. This is a very, very difficult problem, which a lot of smart people have been working on for several decades now. But I still just sort of want to give you a little bit of motivation, because there's a whole host of statistical methods. So for example, like maximum likelihood or maximum parsimony or Bayesian methods, where they're trying to sort of optimize some kind of criterion. And then there are distance-based methods where you basically position sequences that are closely related under the same node with the same branch lengths, where the branch lengths here basically correspond to the distances between sequences. So these two methods are very different in spirit. And it's also known that finding the optimal entry is a basically an NP complete problem. So you have these two sort of tree reconstruction methods, which are very different in nature. And then we also know that these methods, even among themselves, they're extremely sensitive. So essentially, if you have some sort of like measurement error, if you basically these input sequences alignments are basically kind of shifted a little bit, or you kind of have something which goes a little bit wrong, then basically the output tree that you're going to get in the end is going to be completely different. And so it's very, very sensitive to this. So given this, one of the questions you might want to ask is sort of, what's the best tree reconstruction method? Is it statistical method or distance-based methods? How would you compare these methods? And so essentially the one way that you would do that, one way to do that is basically, how do you compare these resulting trees that these methods produce? So that's sort of the driving motivation behind a lot of my work. But you can kind of like extend this more broadly. So it's not just sort of comparing two methods, two trees reconstructed by two methods, but the question then would be like, okay, what do you do if you have a set of trees? How would you compare sets of trees? Other statistical questions you might want to ask is, what is a typical tree, right? So what is, if you had a typical tree from this kind of process, what would it look like? How do you do statistics with these samples of trees? So so I'm going to overview the way that it's very, very popularly done now. So I would say probably the first geometric construction, which is very, very kind of intuitive and elegant. But then I'm going to also give it another perspective to it, which is what I'm working on, and then sort of overview some of these recent results in tropical geometry of tree spaces that I worked on together with some collaborators here. So if you want to compare a phylogenetic tree, you need a similarity measure, right? So this is a distance. So in mathematics, this is really a distance that we're looking for. So from biology, there's a lot of people who work with distances between trees. So these are mostly inner product based distances. So the most popular one is known as the Robinson-Folds distance. And the idea here is basically they want a distance which sort of preserves the inner product property, and is similar to the Euclidean distance here. So this, however, is actually known to be quite difficult to work with, and difficult in the sense where the distances don't behave very intuitively. So if you have like a large distance, it doesn't necessarily mean that the trees are very different from one another. And then it's also known that lots and lots of pairs of trees measure the same distance from one another. So it's very difficult to work with this distance. So the sort of answer to this one is a more geometric based one, which is the BHV metric, which is based on geometry. And this was proposed by Biller, Holmes, and Voigtman in 2001, where they're looking at the space of trees as a moduli space. So here what we're talking about is we're talking about representing a single tree as a single point in a space. And then basically you have your space, you have all these points in the tree in your space where each point represents a tree. And then you want to equip this with a metric somehow. And in B-tree space, what they do is they basically consider geodesics between any of these 2 points, which where the length structure then basically induces a metric structure on the tree space. And then after that, you can basically do these kinds of these kinds of analyses that I was talking about before, based on comparing trees, sets of trees, and looking for meaningful statistics. So B-tree space is very well used, very widely used, not only in biology, but it also appears in combinatorics, in category theory, in computer vision, computational biology. It has a very intuitive construction, and it's known to be the current standard for computational studies in tree space, but it does have some statistical limitations, which I will present later on. But first, about BHV space. So there's 2 ways to look at it. So first, I'm going to give you sort of a geometric construction. So the idea here is basically you look at this tree. So we have a figure of the tree on the left here. And the idea is to ignore the external edges. So any edge which connects to a leaf, you basically ignore it. And then you basically just look at the internal edges, which are left, right? So there are most n-2 internal edges. And the idea here is that each binary entry corresponds to a unique point in Rn-2, right? So the sort of positive orthant of Euclidean space of n-2 dimensional Euclidean space, right? So the idea here is that you take the internal edges, and then you take that and you stack each of the internal edge lengths as a component in a vector, right? And then stack the vector, and then basically this is your representation. This is a point representation that you have in your tree. So because there are 2n-3 double factorial different tree topologies, right? So different types of binary trees. If you want to collect this entire tree as a tree space, right, and you assign one to each tree topology, then basically you have 2n-3 double factorial many of these orthants, these positive Euclidean orthants. So the thing that's important to sort of consider is, okay, so you have each of these orthants for each of the boundaries, but then sort of how do you glue them together? So they are glued together naturally because these boundaries between orthants, they correspond to collapsed internal edges. So these are degenerate trees. So basically, if you take one of the internal edges and then basically just shrink it to 0, right, then you're going to get a boundary between the orthants here. And two orthants, they're grafted together along their common boundary if and only if two binary trees share a common degenerate trees. So and the other thing to note about the beach reconstruction is that orthants are always grafted at right angles. So here's an example of how we could graft two orthants in beach tree space, right? So with this tree here, we have 4 leaves. So we have 2 internal edges, which means that we basically represent this tree by a single point in the plane. And here, in this case here, we have only 1 internal edge, right? Because this internal edge here has been shrunk to 0, right? And so in this case here, we basically only have this distance here to represent this tree here, and then similarly we have one on the side here. So essentially, right, we have these 3 different trees, and then the orthant here is basically how we sort of compare this tree topology here with this tree topology here. So this is one important thing to note in BHV space, which is that leaf label matters, right? So tree topology, by tree topology, I mean the shape of the tree, so the branching pattern of the tree is one thing, but also the leaf labeling matters, right? So here, this is how basically you can graph 2 orthants in tree space, and essentially how you would sort of like rectify this common tree between them here with the boundary. So one thing that I also want to talk about in particular is you can think about there's a special object which sort of like you can think about as a skeleton. It really defines beach tree space, which is this link of the origin. So it's this particular set here, right, which is essentially just it's a simplicial complex because basically you can kind of build your tree space by looking at the infinite cone over the set here. And this set is known as the link of the origin, right? So essentially what you have here, so in this case, this is an example for the beach tree space. When you're looking at n-3 leaves, right, you can just basically take these 3 points and then build the infinite cone over each of them, right? And that's exactly what's happening here, right? And so this link of the origin here is really kind of like, if you think about it as the defining skeleton of beach tree space. So given this here, there's also a way that you can sort of build or look at the construction of beach tree space combinatorially as well, right? So for and here you can look at it this way basically also by this is sort of the same by looking at the picture that I just showed you about grafting orthants together. So here we're looking at particular partitionings of leaf sets within the sets of leaves of the trees. And you have a we're going to look at sort of a partition of internal edges, internal edges which define bipartitions of the leaves here. So we have a bipartition which is called a split, right? if one of the you can say that you have splits and that two splits are compatible if one of the following holds. So here's an example where we was looking at just the same examples before. We were looking at two orthents, which are sort of like, I mean, two orthents, and then how they're sort of related to each other by the boundary. So here we have this this split here. So this tree here is compatible with this tree, right? But these two on the other side of each other are not compatible with another. So that, then we can just basically look at flag complexes as tree spaces. So you can construct a flag complex or a clique complex, right, as follows, right? So when each split of the leaf set represents a vertex, and two vertices are joined by an edge infinite only if two splits are compatible. And a k-split simplex is spanned if and only if its k plus one vertices are connected by edges. And each minimal simplex here represents a tree topology. So it turns out that this flag complex here is nothing but the link of the origin, right? So what we were talking about before, which is the skeleton of BHV space. So this link of the origin happens to have homotopy type of a wedge of n-1 factorial spheres, each of dimension n-3, and then each sphere corresponds to the boundary of an icosahedron embedded in BHV space. So in Ln, two facets share a codimension one face if and only if two trees differ by a rotation. So here's a visual example, right? So here in the case of number 4 leaves, right, you can basically completely enumerate tree space and see what it looks like. And essentially here is completely characterized by the Peterson graph. So in this case here, the link of the origin for 4 trees with 4 leaves is the Peterson graph. And so this is what the full tree space looks like on the right. And here's an example on the left of some of the orthents of BHV space. And these ones actually correspond to the ones with the darkened circle on the right here. So let me show you what I mean. So here we have one particular tree topology, which looks like this. And then the two internal edges that we're going to look at are basically this internal edge length, which corresponds to the collection of the 2, 3, 4 leaves. And then here, this internal edge here, which basically is the internal edge between leaf 2 corresponding to connecting to the collection of the 3, 4 edges. Right. And then here, this is compatible here with this orthent because the common boundary here that's joining these two is, again, the internal edge, which connects to the 3, 4 leaf set here. And then essentially, so similarly, you can sort of travel over this sort of selection here of 5 tree topologies in the same manner by going around. So this is sort of how you can sort of like sort of enumerate and characterize a tree space in the BHV setting. So we need a metric, right? So as I mentioned before, we are interested in comparing trees. So if we want a metric in this tree space, it's an implicitly defined distance. So for 2 trees in the same orthent, basically you're just looking at the Euclidean distance between them, right? So this is 2 same tree topologies living in the same orthent, then it's nothing more than the Euclidean distance. If you're looking at trees in different orthents, so this is where it gets interesting, because if your orthents are near each other, right, you're looking at a geodesic. You want a geodesic, which is the fastest way to get from one tree to another. So if the orthents are right next to each other, then the fastest way to get to one from one orthent to the other one is just to simply go through basically the boundary that's separating them, and then you have the fastest way to get to BHV space. But another way to get there, which is not the fastest way in the case of orthents next to each other, is basically going through the origin. So you basically, what this means, remember, is that you shrink all of the internal edges of the tree to 0, and then just re-expand them out into to get to the other tree that you want, right? So here's an example here, right? If we're looking at T2 and T1 and these 2 orthents here, and you want to travel from one tree to the other, right, then the fastest way is just to go through the boundary, right, rather than passing through the origin. But in most cases, if you have trees which are very, very far away from each other, then the the fastest way to get there is basically through the origin, by basically shrinking everything and re-expanding out. So one thing to notice is that because of the fact that orthants are always glued at right angles, we have this gives a particular geometric characterization to this tree space, and in particular, it's a cat zero space, which basically means that geodesics are unique. And then in this case here, there's a polynomial time algorithm which has been proposed by Megan Owen and Scott Proven in 2011, which is still the fastest way to compute the distances between these two, which is polynomial time. So in particular, it's quartic time in the number of leaves. Okay. So before I go to the next perspective, I mean the tropical perspective, which is the one that I'm working in, I want to take a step back and reflect, right? Like think basically on how trees how trees can generate different kinds of moduli spaces, right? So you can specify a tree by all pairwise distances between leaves, right? So one way that you can just write this down is in terms of a matrix, right? Or in particular, right, an upper triangular matrix, because this is it's a distance matrix, right? So because you're looking at just pairwise distances between leaves. And so you have all of this information in this upper triangular portion of this matrix here, right? So one thing that you can do if you want to turn this into a vector is that you can also just basically take all the components of this upper triangular portion of the matrix here and then stack them against each other, right? And you basically get a vector now in R little n, right? So it's like positive orthant of R little n. So essentially, this gives you a natural map, right? This gives you a natural sort of like a embedding into Euclidean space from tree space, right? So essentially what we're looking at is we're looking at this map W here, which maps from, tree representation into Euclidean space. Okay, so now that's what we're at, and this is the question that I want to ask now. So what are the properties of this map, right? What are the properties of this embedding? So the first question that we can ask is this map injective? So this is an important question because we don't want to identify two trees that have different tree topologies. And the answer to that question is no, this map is not injective. So here's an example where you can see this immediately, right? So here, this is the vector representation of the tree in terms of pairwise distances between leaves, as I explained before. And it corresponds to these two different trees here, which have different tree topologies, right? So basically, this tells us that only considering pairwise distances is not enough to determine a tree, right? So essentially, what you need to do is you need to also include the root. So if you really want to fully determine the end tree, the entry in such a way that you have like an injective map, you need to look at the root as well. So this is where we have this n+1 come in here. So basically you consider the root now, and then essentially you do have this map being injective. So this is something that I want to mention, which is that like even though you need to sort of consider the root here, this is actually also it's not too restrictive because you can basically identify a rooted tree with an unrooted tree, right? By basically looking at the root as a leaf with a label 0 and a degenerate external edge, right? So basically the idea here is that you have your tree, right? And then if you were to have another kind of like leaf going out, right, to label 0, but then just kind of shrink it down to the root, then in this case here, we don't have, this gives you a rooted tree, right? So you can go back and forth between non-rooted and unrooted trees. Okay, so now we have an injective map. So now the question is, what is the image of W of this map? So this is an important question because we need to understand what the image of this map is to be able to understand and be able to devise appropriate tools, right? So if it's if the image here is linear, right, then we can basically just use linear algebra to basically devise the right tools, right? We have these sort of like this is what classical statistics relies on. If it's a manifold, you can basically look at theory of differentiable manifolds or Riemannian geometry. And it turns out that the image is nonlinear and non-smooth. So, okay, so what do I mean by that? And let's take a closer look at what I mean. So, we can reduce the dimension of the ambient space, right, that we're looking at here. So the idea is that if we don't distinguish between trees differing by a constant on the external edges, right, then basically what we get is we get something called the tropical projective torus. So the tropical projective torus is a quotient space, which is generated by the equivalence relation where U is considered to be equivalent to V if all the coordinates of U minus V are equal. You can also generate this by a group action. Yeah, so I'm not going to get into that, but essentially you can look at this quotient space, and then basically you can further refine it by looking at this basically a sequence of maps here, right? So you can also further reduce from the tropical projective torus down to this quotient space here, right, where you're looking at this map phi, right, by looking at basically the sum between all of the elements in your vector, right? So you have this sort of sequence of maps which basically pass from tree space to Euclidean space to the tropical projective torus to something that's a bit smaller here. And yeah, this leads to the sort of more idea of how tropical geometry plays into this, right? Especially with the tropical projective torus. So let me tell you a little bit about what tropical geometry is first. So in algebraic geometry, we study the geometry of zero sets of systems of polynomial equations. And in tropical geometry, the polynomials are defined by the tropical semi-ring. And the semi-ring here is basically where you basically have two operations, and the operation of addition is replaced by its minimum or maximum, depending on what sort of convention you're looking at. And then the product between two elements is defined by their usual sum. So you can, using these two operations, you can sort of define functions and polynomials, right? So here's a picture, here's an example of a tropical polynomial, right? So x squared plus 1, it looks like this, right? So because you have these operations, they're linearizing. It's just giving you the minimum between 2x and 1. And how do we care? Like, how is tropical geometry related to phylogenetic trees? And it turns out that they're related to phylogenetic trees by this really elegant results by Bernd Sturmfels and David Speyer, known as the tropical Grassmannian. So there's another way to look at this, but the one that I want to focus on here is the tropical Grassmannian. So tropical polynomials, you can basically just write them in full generality, right? By replacing the operations, as I mentioned before. And you can look at the tropical hypersurfaces, which is the set of all elements, right? Where your function is at least twice. And you can look at the real and tropical Grassmannian, where you're looking at basically the Grassmannian, which is basically an important projective variety in real algebraic geometry, right? And then if you tropicalize that, right, by replacing the polynomial by its tropicalization, and then the vanishing set of intersections of tropical hypersurfaces, then you get the tropical Grassmannian, and that's what this is here. So visualizing the tropical Grassmannian, so what does this actually look like, and what does it mean? So if we're looking at the sequence of maps that I was telling you about before, right, we know that the image of the tropical Grassmannian in the tropical projective torus is a fan. And then in the image of this fan, right, in the quotient space with the image of phi that we were looking at before, right, then it gives you another fan. And then basically if you intersect all of these with the unit spheres, right, then you basically get this polyhedral complex. And it turns out that it coincides with BHV space, right? So it basically corresponds to BHV space and the link of the origin. So maybe I'll show you rather an example, which might be easier to look at. So if you look at G24, it's given by this hypersurface here. And another way that you can look at it is that it consists of points such that at least one of the following systems of equations holds, right? So for each system here, equality determines a 5-dimensional hyperplane in R6. Inequality determines a closed half space in R6. And then their intersection here is isomorphic, right? So the intersection of the system is basically isomorphic to R4 cross R. And G24 is the union. So, I mean, since there are 3 systems here, basically, G prime 24 is the union of 3 copies of R4 cross R glued along this line here. So essentially what you have is you have, 3 basically rays, and you have the G24, which is 3G triple prime 24 consists of 3 points, right? So here's how you can look at it, right? You have the tropical Grassmannian, and then you're looking at your sequence of maps here, and then essentially you just land on VHV space and the link of the origin. So one thing to point about trees in particular and why trees are special, right? So when I was looking at this map W that I was telling you about that we're studying here, we had this distance matrix, right? So here it's not any old distance matrix, right? Because then in that case you could just sort of look that for anything, but it has to be a distance matrix for distances between trees. I mean, basically pairwise distances between leaves on trees. So in order for that to be true, you need to satisfy what is known as the 4-point condition. So a graph is a tree if and only if it satisfies this 4-point condition. And what the 4-point condition tells you is that basically you have these sort of Pluker relations, right, which are basically the distances between your leaves, right? And if the max, if the max between all of these is achieved at least twice, then you have a tree, right? So essentially, if you're looking at this 4-point condition, this 4-point condition here is very tropical, right? It's a tree which basically corresponds. I mean, it's a condition to be a tree, which corresponds to being a tropical hypersurface, right? So this is and the other way that if you're looking at it in terms of writing it down in terms of tropical expressions here, this is exactly the defining property of the tropical Grassmannian here. So therefore, the question that we had before, which is what is the image of this map W? The image of this map is exactly the tropical Grassmannian, right? Which basically means that this here is exactly, I mean, the image of our map W is tropical. So a little bit more intuition of this 4-point condition. Let me show you an example. So here's an example tree here. We can write down here what as a matrix what the distance between all these leaves look like, and then remember I was saying we stack them as a vector to get a vector representation, and then we're looking at the Pluker relations between them, right? So these tropical polynomials. Excuse me. And the maximum here is achieved twice, right? So it is indeed a tree. And then you can also write it down as this inequality here. All right. So we have this representation. We have a tree space now. And now we need a metric to be able to compare, right? So here I'm looking at the tropical metric. So this tropical metric is a generalized Hilbert projective metric. And it's basically given by the distance between the max and mins of any 2 elements between 2 trees, right? So essentially, here's an example, right? We have 2 trees here. These are drawn to scale here, and then these are the vector representations here. And then we basically take for each of the entries in these two trees, we basically look at their differences. We take the max. So the maximum distance between is going to be 4 minus 1, which is 3. And then we subtract off the minimal distance, these two trees here is 3. So we can also obtained in isometry with Rn minus 1, we can identify the tropical projective torus equipped with the tropical metric with Rn minus 1 by basically looking at this map pi here. So pi, basically, we can embed it into Rn minus 1, and it turns out to be a linear isomorphism. And you can define a norm in this way. So essentially what you have now is basically you have like a normed linear space, which is moreover isometric, which is nice. But how the so okay, you have this nice representation now, but the question is, does this help us at all? How does this help us in terms of the relating back to BHV space? So what we know is, remember that a normed linear space is a cat K space if and only if the norm is induced by an inner product. And here in this case here, we have a non-linear space, but this is not induced by an inner product. So we basically have Rn minus 1 equipped with the tropical distance, right? By the induced tropical distance. And this is not a Hilbert space, so it's not cat K for any K, right? So you can see that these two spaces here, they're intrinsically different. The tropical geometric space and the BHV space. So I'm just going to go over over some things that are known here, since I have very late because of my technical difficulties. I don't want to keep you over time too much, but one of the questions that I had that we studied with my collaborators is, what's the stability between these two different metrics? So it turns out that we do have stability over these two different metrics. So the two tree spaces, the tropical tree space, which we call palm tree space, and BHV space, are not isometric. So the question now is, what's the what is some sort of notion of stability? How can you kind of compare these two? So and they're comparable in this way here. Where this root of n-1 is the smallest possible stability constant. And this is okay because normally you're looking at trees with fixed number of leaves. So this is okay. And then one thing I wanted to mention also is that this here is sort of like giving us a bit of an we're looking at this very conservatively, because we're looking at the case where we do also look at external edges, because remember, in palm tree space, in the tropical version, we do require the external edges, as opposed to in BHV space, where the external edges are basically ignored. The topology of the two tree spaces. So one thing that I think is rather nice about the tropical tree space, the topology of tree space there is exactly Euclidean. So it's the same Euclidean as in it's the same topology as in Euclidean space. So here's an example where you can basically see this, right? So here's what a ball looks like in Euclidean space. Here's what a unit ball looks like in BHV space, and here's what a unit ball looks like in tropical space here. Okay, so we have this sort of way of looking at comparing the two metrics, and an understanding of what they look like topologically. And it turns out that also we have this kind of like characterization of like these of the space as a complete separable, completely metrizable topological space, or in other words, it's a Polish space. So this is very good for probability and statistics, because basically it means that probability measures distributions, expectations, variances, and all of these kinds of objects exist. And it makes sense to ask and study statistical and probabilistic questions in this setting here. So I want to skip over this because because I still, despite starting late, I still kind of want to try and finish close to time. So as I mentioned before, BHV space has some statistical issues. So two major statistical issues here are having to do with one is called stickiness. So here, this is the problem of basically studying how means behave. And what's known in BHV space is that the fresh-shaped means of trees tends to stick to lower dimensional strata, which basically means that so here's an example here. So if you have these sort of these these weights here on beach free space with the 3 leaves, right? Then depending on where this value A is, right? Then basically you have very, very different values for the mean. And so essentially what this means is that sometimes when you're in the setting, most of the time when you're in the setting and you basically collect lots and lots of different data sets and you try to compute the mean each time, the mean isn't going to change, which is very, very difficult to do statistics with, because it makes it very, very difficult to derive things like central limit theorems and therefore do things like hypothesis testing. On the flip side, in terms of descriptive statistics, one thing that's very difficult also because of the strange geometry of beach free space is that you get unbounded dimension in terms of beach free polytopes. So if you basically have 3 points in tree space, and then you basically connect them by their geodesic, their beach free geodesic, then this resulting shape that you have in when you trace out the boundaries of the edges with BHV metrics, then the dimension of this is basically unbounded, which is problematic in statistics, because it basically means that there's no lower dimensional space that you can then project your data onto to visualize or do anything like dimension reduction. So this is very interesting. I think it's a very interesting perspective in terms of tree spaces and the geometry and what this means for statistics. So I've done a sort of like quite a bit of work in terms of looking at the geometry of this space. So I want to quickly overview what else do we know about this tree space as compared to BHV space. So how do you construct a framework for inference? How do you compute the infinitely many geodesics that there are in the tropical tree space? And how do you define explicit parametric probability distributions? So you can do this using optimal transport, and that's what we've done in this paper from 2021 with my collaborators. The question now then is about like tree topologies in palm tree space, right? So in palm tree space, right, we don't have the same sort of nice organization of tree space based on tree topologies as beach tree space is, right? So the question is like, how do tree topologies behave is a lot more kind of messy. And so here in this paper that we have from 2022, we basically answer that question about how to sort of like look at tree topologies in the tropical geometric setting. And then other sort of more geometric questions, which is like, how do you define curvature, right? And how do you characterize curvature? So this is something else that I've done with my collaborator, Carlos, last year. So just to sort of wrap up, the palm tree space is the space of phylogenetic trees with end leaves, right? It's endowed with a tropical metric. So this gives you sort of like a setting to kind of look at the tropical version of linear algebra. It has nice topological, geometric, and combinatorial properties. So in particular, it means that statistical and probabilistic studies are valid and well-defined. And then some things that I'm working on now with this is basically trying to sort of characterize these Frechet means and compute them and be able to sort of study them in statistical setting. And then trying to look at the application of these phylogenetic trees to different settings as well. So for example, neuronal morphologies, or looking at economics and game theory, where you're looking at decision trees and sequential games, where you basically also have a tree structure here. So I also want to thank all of my co-authors. So I've had the great fortune to work with a lot of very smart and friendly people, and a lot of great people to talk to. So in particular, there's all my co-authors, but also my PhD students, UT, Rowan, and Daniele, whom I work with on sort of tropical ideas. And then some references. And I want to thank you again for your patience for the difficulties I had before, and allowing me to talk about this work today.
Well, Anthea, thank you very much for a very interesting talk. The floor is now open for questions. I had one question about infinite dimensionality of these polytopes. Is this always the case, or are there situations where you have some bound and some
No,
application?
yeah, no, it's known. It's actually, that's one of the sort of main theorems that's also very interesting. That was by Rudy and Bo, who are my two collaborators, with a paper by Berendt, where they're looking at this problem, convexity in tree spaces. And the main theorem from that paper is that there is never a bound. So it's always unbounded. So but I mean, there are different ways that you can go about in the BHV space to get this sort of lower dimensional subspace that you want to sort of project down on. And so this was another paper by Rudy, as well as Tom Nye from Newcastle, that appeared in Biometrica. So it's one of the top statistics journals, where they basically worked very hard to come up with a sort of construction, an appropriate construction to get sort of something nicely behaved so you can project down onto.
Good.
But yeah, in terms of the polytopes, though, the question that you had, no, it's never bounded. So it's a really interesting geometry. It was very surprising.
Yeah, very interesting.
Yeah.
How about some other questions? Okay, if there are no other questions, let's thank our speaker for a very interesting talk under difficult circumstances. So,
Yeah, I'm really sorry again, and thank you so much for your patience.